try to understand the subject and try to summarize your understanding in 1 page or 2 pages of either mind maps, or infographic. Okay, so I will alert that in assignment slot. Okay, I will alert that in assignment slot. But this is not assignment. Okay, this is just merely a revision. Okay, but I put it in a assignment slot, okay, because easy for you to submit. All right. So is that clear? So I want you to go through to the fluorescent material again, okay? Because what we discussed last week actually is not completed, okay? So we still not discuss much, on the qualitative analysis, on the what you call it, factors again, the influencing, the what you call the fluorescent intensity, for instance, again. So take another slot. Okay? So I want you to go through that, okay? Summarizing in the form of infographic or mind maps, okay? But in case if you have any problem, okay, if you have any difficulties in trying to understand the matter, okay, so the material, okay, so please let me know, okay? Even if you think, okay, we need to have more or less online face-to-face, I think we can conduct that as well. Okay, particularly after the study week, after the lecture during the study week, right? Is that clear, Ananda? So as today, we're going to focus on the UV, on the NMR, okay, NMR, the principle of it, okay, and also the hopefully we'll be able to discuss a bit on the proton NMR, but we'll see. Okay, okay, any question before I go further on the NMR spectroscopy? Is that okay? You okay, Ananda?
I ada.
Yes, okay.
Yang infografik untuk fluorescence tu due bila?
Well, maybe I can give you a week. Okay, maybe sampai next week.
Okay.
Okay, all right. Right. So if you are okay with it, I guess so. I think now I'm going to continue on the NMR spectroscopy. Right, I'm going to start by showing a video. Okay, I think that's the best. Okay, and then I will continue. Okay, with the notes. So actually, I already attached with MS Team a few notes. Okay, a few notes. I just purposely make it simpler. I basically distributed. I classified the whole topic into small topics. Okay? So it's going to be much easier for you to refer to. Okay, and then I also put in some videos, okay, for you to go through. Some of the videos we're going to share here, we're going to discuss, and the rest maybe during your ample time, okay, during your free time, okay, you can go on your own. Okay, when I said you need to go on your own, I'm very serious that you should spend time to do that. Otherwise, your knowledge, okay, might be shaking a bit. Okay, your knowledge might not be enough, okay, on that areas. So normally revision will make you, we sharpen your understanding, particularly if you try to refer to some other sources. Okay. Okay, I'll start with the video first.
The essential part of every NMR spectrometer.
Can you hear it, Ananda? Both the visual and also the audio?
Yes, Ayanda.
Okay.
Is a powerful magnet. Inside are 2 coils of wire and a sample tube. The tube spins around its axis to ensure that all parts of the sample experience exactly the same magnetic field. One of the coils surrounding the sample tube generates electromagnetic radiation of constant frequency. The strength of the magnetic field changes during the experiment. As the field strength grows, the energy levels of the magnetized nuclei in the sample split further and further apart. At a certain point, the splitting will exactly match the energy of the radiation emitted by the generator. This makes the nuclear spins in the sample flip to the higher energy level and resonance occurs. Soon they return to the lower energy level and re-emit the radiation, which is recorded by the second coil as a tiny current. The current is then amplified and processed to give the NMR spectrum.
Okay, and then basically, I think based on the group responding, okay, I need to play the video 3 times, okay, for them to not to fully understand, okay, but at least to grab, some concept of it. All right, maybe if I can explain it further, okay, basically, in NMR spectrophotometer, okay, so we need to have magnet. So these are magnet, just to block, okay. And then we have, the coil here, okay, the coil. So the magnet basically, okay, because we need a magnetic field, okay. We need a magnetic field in NMR, okay, to ensure, that the what you call it, the nuclei, okay, will going to align, okay, with the magnet, okay. We're going to explain that later. And then we're having, the what you call it, the coil here. The coil basically is going to generate, radio frequency. Okay, so radio frequency generator. Okay, why this this radio frequency generator actually need, the radio frequency, and radio frequency actually is another EMR, another electromagnetic radiation. Remember last time when we discussed about UV visible and fluorescence, okay, the electromagnetic radiation, okay, that we use in UV visible spectroscopy is actually UV light and also visible light. And in fluorescent, okay, we're still using the same thing, okay, UV light, okay, for the excitation. And also sometimes, the excitation need to be done, okay, in visible light, invisible region as well, okay. But apart from the EMR, will consist, other sources like infrared, maybe X-ray, gamma ray, and so on. So radio frequency actually is another form of EMR, okay, with lower energy. So in NMR, actually we are using radio frequency as a source of energy, okay, to be supplied, okay, to the molecule. So here in the middle here, okay, the one that we put, in the middle of the coil here, actually we are putting our sample. Okay, so we a sample, and your sample you put here, because later on, okay, you need your sample, okay, to be what you call it, to be in the field of magnet, okay, in the center of field of magnet, and at the same time, okay, you want your sample, okay, to be exposed, okay, to the radio frequency. Okay, that's going to give energy, okay, to the sample, okay. And this sample, okay, basically this what you call it, the sample holder, okay, is going to be, it's going to it's going to be circle, okay, it's going to be rotate, okay. So it's going to be rotated, okay, in order to ensure that every single angle, every single surface, of the sample is going to be exposed to the magnetic field as well as to the radio frequency. All right. So actually during the process, okay, the radio frequency will be absorbed, it's like what we discussed, in the UV visible spectroscopy as well. So the radio frequency, okay, will be absorbed, by the nuclei, okay, by the nucleus, and as a result, the nucleus is going to flip. I guess going to flip. So once the nucleus come back, to the original positions, it's going to release, okay, the energy. The energy actually is very special energy. The very unique energy. So that energy is going to produce more or less, electrical signal, and this electrical signal is going to be passed again to the circuit here, Okay, we having radio frequency receiver. Okay, that's going to convert into electrical signal, and then this is going to be amplified, and this is going to be converted into the NMR spectrum. Okay, so once again, so we put our sample inside this container. We put this container, the sample holder, right in the center. Okay, and we have the coil here. Okay, the coil that's going to produce the radio frequency energy, the electromagnetic radiation, and then we're also having the magnetic field. Okay, the big magnetic field here that's going to give the magnetic field, okay, to the system. Okay. So I think I'm going to replay, the what you call it, the video again. So with the brief explanation that I had giving just now, try to relate that again.
The essential part of every NMR spectrometer is a powerful magnet.
Okay, another powerful magnet, actually the essential part of the NMR. Without powerful magnet, okay, I mean, no way, okay, we can measure, the what you call it, the spectrum of NMR.
Inside are 2 coils of wire and a sample tube.
Okay, a coil of wire and a sample tube in between, I mean in the middle.
The tube spins around its axis.
The tube spin, okay, on the axis, mana dia ada axis dia akan spin, keep spinning. Why?
To ensure that all parts of the sample experience exactly the same magnetic field.
Okay, to ensure that every part of the sample is going to experience the same magnetic field. Okay, bila pusing tu dia akan semua akan diekspos magnetic field yang ada.
One of the coils surrounding the sample tube generates electromagnetic radiation.
Okay, the coil is going to generate electromagnetic radiation, H mu ni, photon lah ya, okay, energy.
Of constant frequency. The strength of the magnetic field changes during the experiment.
Okay, and magnetic field akan bertukar, always keep changing. Okay.
As the field strength grows, the energy levels of the magnetized.
Remember, then dia punya field strength grow, magnetic field ni bertambah. Tengok balik.
Energy levels of the magnetized nuclei in the sample split further.
Okay, energy level semakin bertambah. Tengok balik. Okay, energy level semakin bertambah.
In the sample split further and further apart.
Further and further apart, semakin jauh ya. At the same time, actually we are supplying, the energy, the H mu ni we are supplying the energy, okay, to the molecule.
At a certain point, the splitting will exactly match the.
Okay, at a certain point, ada satu ketika, okay, bila dia keep moving ni, bila dia makin besar, at one stage energy yang kita supply ni sama. H mu ni sama dengan energy ni, okay, delta E different ni. Okay, the difference between this gap, okay, sama dengan photon, okay, yang ataupun
energy of the radiation emitted by the generator. This may.
Okay, if that happen, once that happen, we call it resonance. Okay, we call it resonance. Okay, then I mean the nuclei is going to flip, okay, to higher position.
Makes the nuclear spins in the sample flip to the higher energy level and.
Flip tu mana anda dia akan bertukar arah, okay? Dia akan bertukar. Okay, jadi dia akan absorb tu, dia akan flip. Okay, tapi lepas tu dia akan come back to the original position dan dia akan keluarkan, radio frequency.
Resonance occurs. Soon they return to the lower energy level and re-emit the radiation, which is recorded by the second coil as a tiny current. The current is then amplified and processed to give the NMR spectrum.
Okay, another in any instrument, normally the current that being generated is very, very small. Okay, I mean similarly, what happened in UV visible spectroscopy? If you remember, the what you call it, the detector that we use actually is a PMT. PMT stand for photo multiplier tube. Okay, photo multiplier tube. Why we should multiply? Okay, because the photo multiplier tube, basically a tube that's going to multiply the signal. Why should we multiply? Because the signal is very weak. So we need to amplify, okay? Many times, okay, until we get, you know, certain signal that can be measured, okay? Not only can be measured, okay, can produce, you know, some signal, okay, that we can observe. All right. So similarly here, the signal that been generated is very small. Okay, that's why we need to amplify, and finally, okay, it's going to, going to be detected, and finally it's going to produce the spectrum. Okay, I'll stop here. Another, do you have any question that you want to ask? Can you follow? Maybe not 100%.
Yeah.
Okay, at least 50%. You know, from what I'm explaining and from the video as well. Shafika, you anything? Okay, Izyan dia dah faham. Okay, very good. I can ask you later. Shafika, you want to say something?
No, I understand.
Alright, okay, it's good. Okay, so if you understand this, I'm going to show you the second video. Okay, let me right sekejap ya. The second video. This is actually a silent video. The second video ni actually is silent video, no sound at all. I think I just took it somewhere, you know, but I like the animation, okay, because of it showing the real instrument, okay, like the one that we have here in USIM, and how, you know, it's showing the position. Okay, the moment you apply the sample, and then how it position, okay, inside, you know, the sample. That's all. So it's actually a quiet video. Don't worry about that. Just watch. All right. Okay, that's it. Okay, so maybe if I can show you together, maybe with some explanation from myself. Okay, another more or less. Okay, this basically the actual size, you know, of NMR. Okay, the one that commercially available. And why we need a, you know, why the size is really big. In fact, if you can notice from here, they also provide a ladder. Ada tangga ni, okay, for you to climb, okay, up, okay, to introduce your sample. You're going to introduce your sample from the top, okay. This is very big because you need a very powerful magnet, okay. You need a very powerful magnet. That's why, you know, the size actually is very bulky, but I think presentable, isn't it? Just like a robot as well at the same time, okay. Another is just cryoprobe. Okay, cryoprobe actually because of in NMR, I think you aware that we are using liquid nitrogen and also liquid heliums. Okay, so both are basically, you know, in very low temperature. Okay, because we need to cool down, okay, the tower. Okay, so we are using, you know, very high, lower temperature to cool down, you know, the temperature basically to maintain the performance, you know, of the magnet. Okay. So cryoprobe, actually, that situation, when you conduct your experiment in very low temperature, we call it cryogenic condition. Okay, cryogenic condition actually means very extreme lower temperature. So similarly here, okay, we deal with a very low temperature, and we're having some probe here, some sensor if you like, okay, that's going to control or it's going to monitor, I mean the situation, the temperature inside there. So we call it cryo probe. I mean the probe that's going to monitor, I mean the condition, the temperature and so on. And this sample here, okay, the spinner is going to spin basically, as you mentioned in the as you can see from the video previously, the animation actually showed to us that we need to spin. Okay, we need to rotate, the sampler. I mean the sample. Okay, so that the sample will be exposed, consistently, okay, into the magnetic field as well as to the radio frequency. Yeah? So this is the spinner, and the sample is here. Okay. So you put your sample there and introduce your sample. Okay, introduce your sample from the top. Okay, that's why you need a ladder. Okay, to go to the top and to reduce your sample. Okay, suppose you open. Okay, I mean what you call it. Once you open, this big instrument here. Okay, once you open the main one. Okay, that's what you're going to see inside. Okay, right. So you can see basically, the coil here. Okay, the coil like what you saw, just now from the previous video. Okay, here actually the liquid helium. Okay, and then the liquid nitrogen as well. Okay. So liquid nitrogen basically, okay, will be outside. Okay, liquid helium, okay, inside. Sometimes they design it so that helium will be in between, and liquid nitrogen, it will be the inside, okay, and outside, the liquid helium. So, okay, because helium is very expensive. So liquid nitrogen actually basically the purpose is the same to cool down, the tower. Okay. For liquid nitrogen, okay, they put outside, the helium, okay, because in a way it's like to protect the helium, okay, because helium is very expensive. So, I mean, for the cooling, for the outside, we just really depend on the liquid nitrogen, okay, rather than the helium, and the helium focusing, on the inside instrument. Okay, you can see the sample now. Okay, we inject the sample more or less. And now, the magnetic field started. So we have the magnetic coil here. Okay, so that's going to produce, the magnetic field. So now actually the sample will be exposed to very strong magnetic field. Okay, so you can see inside, the radio frequency. The radio frequency is going to supply, the EMR, the electromagnetic radiation. If in UV visible, actually we're having UV lamp. Okay, we also having a tungsten lamp. Okay, for the EMR. Okay, of visible and also UV. But here we are using coil. Okay, to produce the radio frequency. Okay, and supply this EMR. Okay, to the sample. And here basically the molecule, the sample that we want to study. So here actually the molecule. And now we excite them, okay, we excite the atomic nuclei, okay, by using radio frequency. So RF excitation. Okay? So we excite them by using atomic nuclei. Sorry, we excite them by using radio frequency. Okay. Right, okay, that's about all. It's very simple video, very good animation, so that it will assist you to understand further. Any questions so far, Ananda? Okay. Right. Okay. Silent means okay, you're happy with it. Okay. Actually, I have another video that I want to show, but before that, I think it's better, I go to the slide first. All right, okay. So mass spectroscopy, the introduction. Well, some theory about it. Okay, so partly we already watched, the video, but I think so by now you're having some very basic understanding. NMR actually is a spectroscopic technique, I guess, like UV visible spectroscopy, like fluorescence spectroscopy, like reflectance spectroscopy, and other technique. So, but in this case, actually, for this NMR, we're going to get information about the number and type of atom in the molecule. Okay, imagine we are having, maybe a molecule. The molecule will contain, some atom, maybe carbon, as the backbone, maybe hydrogen, maybe oxygen, maybe heteroatoms, okay, and many others. But in this case, we're going to focus only on the NMR proton and NMR carbon-13. Okay, these are the two commons. Okay, NMR technique again that been used in many labs. Okay, so I mean by using NMR proton and NMR carbon-13, we are able to know the number. I mean the number bilangan dia, the number of hydrogen atom or the number of carbon atom, for instance, in a molecule, and also the type of atoms. Okay, and the type of atom, whether the atom actually is because even though we are dealing with the same atom, okay, for instance, we are dealing with carbon, okay, but the carbon actually different from one another in the sense that they experiencing, okay, the difference environment. Okay, so for instance, maybe the first carbon, okay, maybe attached to oxygen, or maybe surrounded, okay, by another metal group, okay, for instance, okay, or maybe the other carbon, okay, will attach directly to maybe chlorine, okay, for instance, okay. So even these two are still carbon, but since they are exposed to different environment, they will also behave differently. Okay, when we study the NMR, proton or maybe carbon-13, so we'll notice that they're going to produce different signal. Okay. So the same atom, but they are at different position, okay, with according, to the surrounding, they're going to produce, okay, the different signal as well. Okay, that's unique, mashallah. Okay. So NMR is used to characterize organic molecule by identifying carbon-hydrogen framework within molecule, because we know that once we're talking about the hydrocarbon, okay, like in organic study, okay, like in organic subject, you study a lot of hydrocarbons. So hydrocarbon actually derived from the word carbon and hydrogen, isn't it? So that's why the application of NMR actually is a lot, okay, in organic chemistry, okay, to determine, okay, the structure of the molecules, okay, for instance, okay, because by using NMR we are able to identify, the carbon hydrogen framework on how they've been organized, or they've been how they attach to each other. All right. Okay, so right, nuclear magnetic resonance, okay, they call it NMR, or nuclear magnetic resonance. Okay, so nuclear referring to the nucleus of the atom. Okay, magnetic, okay, because involve very powerful magnets. Okay, so we need magnetic field, I mean in trying, okay, to get, the signal out of it. And resonance also, I mean one of the characteristics of the nucleus. So they call it NMR, okay, because of we need magnetic, I mean to get a signal, and we are dealing with the nuclear, okay, with the nucleus basically, okay. That's why they call it nuclear, and it's a resonance, okay, because I mean like from the video you saw just now, okay, so I mean we keep supplying, the regular frequency, and at the same time we apply, the magnetic field. So until at one stage, the resonance is going to occur. So that resonance, okay, that's going to be a monitor, okay, by by the instrument, okay, because that's going to give us, some information, about the energy which related, okay, to the atom, okay, either carbon or the hydrogen. Okay, NMR, we're having two types. Actually, we're having more, okay, but the most common one actually is a proton NMR, which used to determine the type and number of hydrogen atom in the molecule. And carbon-13, which is used to determine the type and number of carbon atom in the molecule. Okay, so a proton, okay, for number of proton and type of proton. carbon 13 for number of carbon atom and also type of carbon atoms, right? And the soft energy that we use in NMR, like what you saw from video just now, we are using radio wave, okay, radio frequency. Okay? And I mean, from this, okay, we know directly that it's going to involve very low energy and frequency, isn't it? All right. Because surely, you know, the energy is going to be less, okay, than the energy that we use in fluorescent. It's going to be less, much less, okay, than energy that we use in UV visible spectroscopy as well. Okay. In fact, it's going to be less as well compared to the energy that we use, you know, in IR spectroscopy. Because in IR, basically, it's involved, you know, the vibration, which needed, you know, which need a bigger energy. Okay, but here, okay, we just involve the rotation of the nucleus. Okay, and less energy actually is required for that. Okay, when the energy radio wave interact with molecule, they can change the nuclear spin of certain atom in presence of strong magnetic field. All right, like you saw from video just now. Okay, skip this. Okay. Nuclear spins are oriented randomly in absence, okay, here referring to this one, okay, the green one, of an external magnetic field. Okay, I mean without magnetic field. So basically, you know, the green the nuclei here, okay, representing, you know, the direction which is at random. Okay, so without the external magnetic field, basically the orientation actually is in random. The orientation of the nuclear spin actually is randomly distributed. Okay, randomly distributed. Dia tak ada certain direction. But the moment we apply, you know, the external magnetic field, okay, so immediately, okay, I mean the nuclei is going to be aligned, either aligns, okay, in the same direction, like the pink one here, okay, the pink one here, the pink nuclei here actually representing, you know, the same direction, okay, meaning they're going to spin in the same direction, which is less energy, isn't it? They just follow the direction, okay, the as-in direction, so less energy is required. Or another alternative, okay, basically, you know, like the blue one, okay, I mean they still align, but at different direction. But dia menentang arus, different direction. So this going to have a high energy, okay, because what? Because they need to move against, you know, the direction, okay, the direction of the magnetic field. Okay, they need to move against, and therefore, okay, they need higher energy. But most of the nuclei, okay, most of the nuclei, okay, they're going to have, you know, the same direction, like you know, like the external magnet, right? So we're not representing, you know, the magnetic field, okay, from the external sources. Okay, some nuclear spins are aligned parallel, okay, to the external field. Okay, ini parallel, yang merah ni parallel. So it's going to have lower energy and more likely, meaning majority of the nuclear spins, okay, is going to have you know, position like this. Okay, so many of them. Okay, so very small portion, very small amount that's going to have, okay, different direction. Okay, or anti-parallel we call it. Some nuclear spin are aligned anti-parallel to the external field, so we expect this to have high energy and less likely, meaning not many of them, okay, not many of the nuclei is going to have, you know, this unparalleled anti-parallel direction. Okay, this slide basically still showing, okay, the same concept, okay, the same understanding, just I'm putting it differently, okay, so that you can understand, okay, further. All right, so this has to do with the magnetic field. Okay, so you will see that most of them is going to be in line, in parallel. Only few is going to take, you know, the anti-parallel alignment. Like without the magnetic field, okay, so the nuclei spin actually, you know, on the random direction. So as a result, so we can assign basically the proton, for instance, okay, to have spin plus half and spin plus half, plus a negative half. Okay, so I mean the one, okay, the one that align, okay, with the one that having, you know, the lower energy because they align, you know, with the magnetic field. So we assign them with positive half spin. Okay, the one that having higher energy, that anti-parallel, okay, with the magnetic field, with the external magnetic field. So we give, you know, we assign them as negative half spin state. So as simple as that. So positive meaning they align, lower energy, a negative spin, okay, so high energy, and the anti-parallel. So still the same thing, okay. So we're having, you know, the random spin, the nuclear spin random, the random nuclear spins, and then, okay, the moment you give the energy and also, you know, the magnetic field, we can have, you know, two different situation. Okay, the one which is aligned, okay, we not with the magnetic field, we call it, okay, parallel, and the one which oppose, you know, the anti-parallel, okay, from V naught. Okay, so this actually having high energy, you know, the one the align having lower energy. And then, you know, we also call it, you know, beta spin state. Okay, the one with lower energy, and we assign just now positive half spin state. Okay, we also name it as beta spin state. Okay, the one which oppose, okay, we call it, okay, alpha spin state. Okay, so random by applying magnetic field, so it become parallel. And, you know, once you apply, you know, the energy, okay, so they are ready, okay, to do the excitation. Okay. Okay, this like what you saw in the video, another. So once you, okay, once we increase, you know, the magnetic field, okay, I mean, the distance here, the delta E between, I mean, the difference between high energy state and low energy state is going to, or delta E is going to increase as well. And at one stage, you know, I mean, the RF frequency, the radio frequency that is supplied, again, to them is just enough. I mean, to have equal amount, okay, of energy like what we have in the different here. If that happens, so we said that the nucleus is going to resonate, okay, and it's going to flip. It's going to flip, you know, from this position and become this position. But the condition is this not very stable, okay, and they I mean, the nucleus actually is having, you know, the high tendency to go back to the original position, okay, by releasing the energy. And then energy basically can be detected, okay, can be supplied, can be amplified, and can be detected. And the detected, okay, signal, okay, actually will correspond, okay, to that particular atom, and actually it's unique to that particular atom, okay, depending on the surrounding of the atom. Okay, I mean I mean, depending on the presence of other atoms, okay, in the I mean, surrounding, you know, the particular atom that we are interested in. Right. So this summarizes everything, okay, more or less. Under, so we have the energy here, we are having the upper magnetic field. Now we know the delta E, and here we're having, you know, the plus, the magnetic, sorry, the spin, okay, the magnetic field, plus half and negative half. You know, this is called a beta spin state, alpha spin state. This is actually lower energy, higher energy. Okay, I mean, just as an example, you know. Okay, for 300 megahertz, okay, for instance, okay, N beta over N alpha, you know, for 2,000, for 2 million nuclei, okay, we notice, okay, that the ratio more or less is equal to 1. Okay, very few. So only 48 actually excess of nuclei in alpha spin state. Okay, so therefore, basically, we will notice here that, you know, the NMR actually is inherently, insensitive technique, but nevertheless, it's going to produce, the very useful, what you call it, signal, okay, that can furnish us, with the information that we required. Okay? So again, with the energy, flipping is going to occur, and after relaxation, okay, flipping is going to occur. Just going to be excited, and after relaxation, okay, basically it's going to come back, okay, into the original position. All right. Okay. This what happened another during the flipping. Okay, from one spin, okay, to the other. Okay, from plus half to negative half. Okay, so here actually the original position before the flipping. Okay, so you will notice that the cone here actually, the what you call it, the rotation actually is anti-clockwise. Okay, anti-clockwise. Okay, so this is actually the axis of precision, sorry. And then this is the orbit. And actually we're supplying, the radio frequency. Okay, radio frequency here we're supplying. And once the frequency is the same, like the difference in the delta E in the energy of the nuclei. Okay, this is going to do the flipping. Okay, it's going to change, okay, the flipping, and now, okay, it's going to do the rotation, okay, which is following the clockwise. So clockwise rotation, this anti-clockwise, this clockwise. Okay, and initially we start with spin plus half, and now becoming spin and negative half. Okay, all right, this what happened. You can see, you can imagine, the rotation. Okay, the spinning charge of a magnetic field. And as a result, we can have a negative half, sorry, positive half. And once energy absorbed, again, the flipping one is going to occur, and we're going to have the negative half. Okay, another. All right, this is somewhat the same thing as well. Okay, so lower energy state, you actually a high energy state. Okay, so energy will be absorbed. Okay, absorbing radio frequency radiation causes the nucleus to spin flip. Okay, from here, it's actually the original position, positive half, now becoming negative half. Okay, but this is not stable. High energy state, again, not stable. It tend to move back, okay, to the original position like this, and it's going to release the energy. The energy is going to be absorbed. Okay, going to be detected, okay, by the detector. Okay, like what we saw in the video just now. Okay, we're having the magnet here. Okay, so we're having the coil, the radio frequency generator. That's going to supply the radio frequency. And we put the sample in the middle, I guess, so that the sample will be exposed, and this keep rotating. We keep rotating the tubes, okay, of the sample. So this will expose the sample, okay, into the magnetic field as well as the radio frequency. Okay, once flipping occur, and once the molecule resonates, okay, so the amount of energy that has been released is going to be detected. Okay, going to be detected, amplified, detected, and finally it's going to display the spectrum of NMR, okay, that contains some information, okay, about the atoms of interest, either carbon or hydrogen. Okay, only not many nuclei SCB NMR phenomenon. Okay, so basically only nuclei with odd numbers of proton and nuclei with odd number of neutron. Okay, it's going to inhibit. Okay, it's going to give the resonance. Okay. So you can see from the magnetic nuclei, okay, this non-magnetic nuclei, yeah, right? So what we focus actually on the proton and also carbon-13. Okay, that's the first slide. Ananda, if you have any question to ask. Any question, Ananda? Can survive? Can I proceed? Okay, yes, please.
Kan kita ada alpha state dengan beta state kan. Yang beta spin state tu dia ikut arah magnetic field eh?
Tak yang
Terbalik.
okey. Yang ikut magnetic field itu adalah yang rendah. Okey, yang alpha. Beta dia
Yang alpha.
against. Anda kena ingat macam ni je. Anda kena ingat macam ni. Dia kalau dia ikut arah magnetic field, okey, dia akan follow je arah tu. Betul tak? Jadi maknanya dia mudah untuk dia excite sebenarnya. Perlu energi yang rendah. Tapi kalau dia go against magnetic field, mana direction tu dia against. Jadi kat situ, dia perlukan tenaga yang lebih. Okay, imagine macam ni. Anda pernah tak buat apa ni, ya macam canoeing, okay, canoeing. Ataupun water rafting, the best example. Water rafting, air sungai mengalir, okay. Kalau kita just follow aliran sungai tu, arus sungai tu, kita akan mudah. Kita cuma dayung tinggi tepi-tepi saja kan, untuk elak langgar jeram depan tu kan. Tapi kalau kita buat dalam water rafting tu, kita go against, okay, the sungai punya flow. What happen? Okay, akan penat gila lah, betul tak? Because you need to you need to spend a lot of energy, okay, because kita menongkar arus, okay. So you need to survive, okay, you need to really, use your energy, okay. Sometimes a lot, okay, in order for you, okay, to make a progress. I guess so similarly, clear, okay. Once you go against, the direction of the magnetic field, then you need high energy. So high energy tu maknanya dia adalah dia adalah beta lah, okay. Dia adalah beta spin state, ataupun kita akan assign dia sebagai negative half, okay. Dia ni high energy. Okay, boleh faham?
Okay.
Okay. Okay, anak dia. So kalau okay, so I ada proceed untuk maybe on the another slide, and then mungkin tunggu video, and lepas tu rasanya habis dah. Alright. Tak mau panjang-panjang, nanti pening. Okay, now on the instrumentation. Okay, instrumentation tadi dah nampak dekat video sebenarnya instrumentation dia. Ada tak sini? Ada instrumentation ni. Okay, basically you are having, dah cerita tadi tak cerita lah. So sama lah ni, magnet, okay, you have a coil, okay, you have, the, what you call it, ni the principle lah, okay, ini dia punya sample. Tadi dalam yang besar tu, you can see from the bigger, yang video tadi, the bigger instrument. That's why, okay, we need to introduce this, from the top, okay. Yang besar tu because basically they try to house, the powerful magnet ni. Right, so the same thing has also been shown, okay. Right, tak apa. Ada tak boleh hafal. Alright, instrumentation. NMR spectroscopy, okay, technique based on the absorption of EMR in the radio frequency region. Okay, radio frequency we're talking about the, from ranging from 4 to 900 megahertz. Okay. So in fact, for the instrument that we have, you will see that, like some instrument actually we are using 300 megahertz. Some instrument actually we are using 900 megahertz. Itu yang paling powerful lah. Okay, 300 megahertz. Alright. So, but still within, the radio frequency punya range. Okay. So NMR proton, okay, proton NMR is one of the most powerful tool for elucidating the number of hydrogen and proton in the compound. Okay. So proton NMR, okay, so far actually they're very powerful instrument, okay, in order for us to determine the number of hydrogen atom available in the molecule, also the number of proton sama lah, okay. So the number and also type, okay, the number of hydrogen and the type of hydrogen, okay. Alright, so basically determine the physical and chemical properties of atom molecule in which they are contained, right? So because even though we are dealing, with the same atom, carbon or hydrogen, but these two atoms, okay, even though they are the same, okay, carbon dengan carbon, for instance, hydrogen dengan hydrogen, but since they are in different environment. Okay, suppose you put them in different environment, or they come, from different environment, meaning, I mean, the nearby atom is different, okay, from each other. So that's going to give a different signal as well. Okay, can provide detailed information about the structure, the dynamic structure. Okay, contohnya mungkin aliphatic. Okay, and also maybe benzene ring. Okay, so I mean the information will be different. Okay, I mean the signal will be different. The dynamics, okay, the reaction rate, okay, that occur, and the chemical environment of the molecule. So this is going to more or less govern, okay, I mean the signal, okay, that going to be generated, okay, by the carbon or proton. So basically, the method can be used, okay, to study variety of nuclei, okay, but in our case, we focus on the hydrogen or proton and also carbon 13. Okay, simulation, I skip this. Okay, I skip this. Okay, see, still the same thing, okay, but different, been presented differently, okay, but more or less the setup is the same. We have the magnetic here, okay, that's going to give, very powerful magnetic field. So we putting, the sample tube, and then actually we're going to supply, with the radio frequency. So we're having the different transmitter here, and also the detector. And similarly, okay, we also having, the controller for the magnetic field. Okay, we can control the magnetic field. Okay, how strong that unit. And finally, okay, we have recorder that's going to record, the signal, okay, that coming out, from the instruments. All right. So the same thing. Okay, we have the magnetic pole here, very big magnetic pole, very powerful. Okay, and then we having, the frequency, what I call it, generator. Okay, generator, and also the receiver here. Okay, and we putting, the sample inside, in the middle here, and we spin, okay, the sample tube, okay, so that it can be exposed evenly, okay, to the magnetic field here. Okay, right. Okay, this another. As I said just now, okay, the radio frequency can vary, from from 4 to 900. Okay, so similarly, okay, depending on your budget, okay, you can buy either 900 megahertz or maybe 600 megahertz or maybe 300 megahertz. Okay, yeah. Here we're having 300 megahertz, and this one actually 900 megahertz. So I mean the more powerful, okay, the bigger the size is. But nowadays, you can see that the size also very, even though it's a big, okay, but look nice, okay, very presentable. But like in this case, it's like a robot. Okay, so this was the most common. Okay, 300 megahertz. Okay, but not as powerful as, the 900 megahertz. So again, okay, so what inside here basically is the same concept. Okay, but here actually the magnetic field actually is more powerful. And here actually bigger size, and that's why they having, this ladder. Okay, so that, the scientists, okay, can just really climb and introduce the sample, okay, from the middle here. Okay, the common working bench, okay, or the light, the light setup, for the NMR. So again, like we mentioned just now, okay, we're having, the sample tube here. If you open this, okay, you will see, more or less, this is the situation. Okay, what really happened, inside here. And then you need to introduce your sample from here. The sample is dissolved in solvent in a thin NMR tube and placed in a magnetic field. Okay, so you just simply prepare your sample, and then, okay, introduce, the tube, the sample tube, okay, inside from the top, okay, inside, inside this chamber. Okay, so in the NMR probe here, the sample is rotated in a magnetic field and irradiated with a short pulse of RF radiation. All right. So we put in the middle so that it will be exposed, to the magnetic field. At the same time, okay, we supply, the EMR, the electromagnetic radiation, which is, in this case, we are using radio frequency. Okay. So finally, the process, the amplification and so on, and, the MR spectrum will appear here. Okay. So RF pulse, radio frequency pulse at specific frequencies and duration are pulsed at high energy into the sample, which sits inside the probe, inside the magnet here. Okay. tiny current are then picked up by the receiver. Very tiny current, okay, going to be picked up. It's not shown here, somewhere in here. Amplified and digitized into a signal ready for post-collection processing. Okay, so going to produce, the NMR. Okay, if you take a magnetic cross section another, this what you're going to get. Okay, basically again the sample ball here in the middle. Okay, the sample here, the probe. So we're having the coil. Okay, and also the magnetic field here. The magnet. Okay, the rows we having the cryogenics. Okay, cryogenic condition. Okay, very cold. And we having, here the green one, basically liquid helium. Okay, liquid helium is here, liquid helium. Okay, the purple one actually, the superconducting coil. What I'm trying to show basically the helium and the liquid helium, the green one. Okay, is going to be adjacent to it. Okay, we having both. In the inner part and the outer part, okay, we're having, the liquid nitrogen. Okay, so we're having liquid nitrogen here, liquid nitrogen. In the middle, we are having, the liquid helium, because helium is very expensive. Okay, so more or less, the nitrogen here will also help, the helium to maintain the temperature. At the same time, liquid nitrogen is going to, to absorb, all the heat, that might occur, at the outer of this, of this human. Okay, so we try to go to every single component of it. Okay, every single component of of the instrument. So we're having a magnet. Okay, so we're having a magnet. So magnet will provide a stable and homogeneous field, capable of producing strong field. Okay, from 600 to 100 megahertz. Sample holder, okay, so can accommodate 1 to 30 milligram sample. Okay, but we can also dilute the solutions again, depending on our needs. Solvent that we use should not containing any hydrogen. Why? Because we want to determine the hydrogen in the molecule. So I think if our solvent also contain hydrogen, so we don't know whether the hydrogen that we detected, whether is it coming from the solvent or is it coming from the from the molecule. Okay, so that's why it's important for us to remove any hydrogen from the solvent. So the glass tube basically, diameter actually is very small, 5 millimeter. And the length ranging from 15 to 20, centimeter length. Okay, that's why it's a bit high. And the frequency oscillator, this is going to produce, the frequency of, for the EMR. Okay, that's going to be transmitted into the sample and installed perpendicular to the magnetic field. Okay, detector and receiver. From the name, you can guess. Okay, basically it's going to receive, the signal. Okay. All right. Is tuned to the same frequency as transmitter. Okay, we know that. When a processing frequency is matched with RF, the nuclei induced in detector call and this sample and sent to recorder. Well, actually, we understand that once it's meshed, once the RF that we supply is matched with the energy, okay, of the nuclei. Okay, so what happened is, resonance going to occur. It will resonate. So, the molecule is going to resonate, and that energy, going to be relieved, and it's going to be detected again, by detector. Okay, recorder is going to give a spectrum, the one that we use, for our analysis. Okay, some tips, working of NMR spectrometer, working of NMR spectrophotometer. Okay, so the sample, under investigation are taken in a glass tube because of transparency. RF source is made to fall on sample by feeding energy into the coil wound around, the sample holder. I think as you can see, just now, from the previous slide, we can see that. Yeah, okay. So the call here, the wire here actually is going to call, the sample. So similarly here, okay. So I think the wire is going to call, the signal. Sorry, the tube. So RF source is made to fall on sample by feeding energy into the coil wound around the sample holder. Okay, they purposely, attach, the wire, okay, on the surface on the sample holder. A signal is detected of if a nuclei in sample resonate with source. Okay, that's what happened. Okay, from the video you can see that as well. Energy is transferred from via nuclei to detector source. Output detector is fed to the record of amplification. Okay, and finally we're going to get the spectrum. Right. Solvent should not contain proton. Should be cheap. Okay, inexpensive. Should be low boiling point and non-polar in nature. Okay, so generally we are using deuterated chloroform, okay, CdCl3, used as a solvent. If the sample is solvent in polar solvent, so these are basically some of the solvent that can be considered, okay, to be used. And finally, another, what's important actually the internal standard. So we need to have kind of reference. Okay, once we run, the sample, we need a kind of reference. In this case, we call it internal standard. And we are using TMS, okay? This is TMS, as a reference, tetramethylsilane, okay, tetramethylsilane. So tetramethylsilane is most commonly used as internal standard for measuring the position of proton and carbon-13 and also silicon-29, okay, but we are not going to discuss about this in NMR spectroscopy. And the reason why we choose TMS, okay, as our internal standard, at first because of the chemical enough, okay, chemical meaning it's not going to react, with most of the chemical, okay, because as a solvent, the solvent should be enough. The solvent should just merely dissolve, the sample and not taking any chemical reaction in it. Secondly, miscible, okay, meaning it can form just a single layer, okay, with a large array of solvent. So how many protons that we have altogether here? Okay, we have three. So we have total 12 protons. Okay. So is 12 protons are all magnetically equivalent. Okay, so because of symmetrical, all right. So we're having CH3 here. So actually all actually equivalent. Even though we have 12 proton, but all of them actually is similar in nature. All right. As a result, this is going to strengthen. Okay, because the surrounding is the same. We're having 12 proton, but the surrounding is the same. So this going to produce one very strong signal. Okay, so its protons are highly shielded and give a strong peak, even small quantity. So you can see from here, the signal is very strong. TMS is very strong, all right? And it's single, on the single. There's no. It's like the rest. Okay, maybe you will have splitting like this, but here actually just a single. Okay, it is less electronegative than carbon. This is some of the characteristic why we choose TMS. Highly volatile and can be easily removed to get back sample. So volatile, supposedly you want to get back, the sample from the solvent. You can do that, okay, by merely heating it, all right, to remove, the solvent. Because some sample could be very expensive, okay. So that's why maybe we want after the experiment you want to recover back, the sample. You can do that by TMS. It does not take part in intermolecular association with sample. Okay, so just now we mentioned that this is actually inert solvent. Its resonant position is far away from absorption due to proton in most organic molecule. Okay, so you can see, that the resonance, okay, of TMS, okay, is far away, okay, from, meaning it's quite a distance, from the rest of the molecule. Okay, so that's where you can see, the distance here is quite a distance. It's quite a distance. So we assign them with TMS equivalent to 0. Okay. So that's about all, Ananda. If you have any question, you can ask. Otherwise, I'm going to stop here. And please, okay, have a look, okay, to the metro, okay, that I have, okay? And I think the what you call it, the class representative, okay, need to what you call it, furnish me with the information, okay, regarding did I mention just now about the tutorial? Did I mention that? Or maybe I missed out, with the first group. Not sure, isn't it? Okay, I mean, you have finished your tutorial, is it, Ananda? Sorry, you have finished with your lab session, not tutorial, lab, your lab work, isn't it? Last week is the last one, isn't it? Okay.
Yes.
Yeah, okay. Because actually we need to use, that slot, okay, the time slot. Okay, this is what Cik Wan Zanaria, okay, Prof. Cik Wan Zanaria told me. We need to use, that Amali slot, okay, that lab slot, okay, for our tutorial, okay. Because actually, we expect, okay, because, for the UV visible spectroscopy, the fluorescent, and, for the NMR, actually, these are tools, okay, for us to use, for structure elucidation, okay, as well as, for the quantitative, okay, analysis. Okay? So I think in order to assist you, with the final, okay, and in order for you to understand for you to having better understanding regarding the subject that we already discussed. So I need this slot, okay, maybe I need about 1 hour, okay. And during this 1 hour, basically, I'm going to give you, the question for the tutorial. And if possible, I want you to work in the same group like the group that you have in your practical, okay. And then after the briefing session, I'm showing more or less, what to do, how to tackle the question and so on. Then I'll leave you in peace, okay. And then I want you to submit, okay, basically, the tutorial, okay, maybe within a week, okay. So with the first group, okay, initially they agree, okay, to have, the tutorial tomorrow, okay, 10 o'clock. But just now, I think Afiq, okay, just mentioned to me that they're going to have it, okay, next month. Sorry, next week. Because next week actually the final week. Okay, the final week. So I don't know. I leave it to you. But the first group is going to have Tuesday next week at 10 to 11. If you want to have next week as well, so it's going to be 11 to 12. All right. Okay, Ananda, I leave it to you. All right. So, is there any burning question that you want to ask, okay, regarding the introduction on the NMR spectroscopy? Hopefully, next week we're going to discuss about the what you call it, the chemical shift, and we're going to discuss, okay, about both the in detail, on the carbon-13 as well as the proton, okay, on how to use to relate, the splitting patterns, okay, of the spectrum, okay, with the number of proton or the number of carbon and so on. All right. Okay. So I think that's about all. Okay, so but I need information, okay, from you. Okay, I need somebody from you. Asfa, are you there? Asfa?
Yes.
Okay. Okay, can you let me know, okay, whether your group prefer to have the tutorial tomorrow or next week? If next week, the time available only 11 to 12. All right. Okay. Okay. All right. So I think that's about all. Kalau tak ada, I think we're going to end, our session today, okay, by reciting tasbih kifarah and also surah al-asr. Subhanallah wa bihamdihi, bismillah wa bihamdihi, asyhadu an la ilaha illa anta, astaghfiruka.